Okay. Good day, everyone. I think we have people from all over the world. So good afternoon to some people, good morning to others. Hope everyone's having a nice morning. Very excited to have I'm going to go full screen and make sure the slides are sharing okay first. Um, is that looking okay? Someone give me a thumbs up or just to say yeah. Okay, great. Thanks, Alex. Um, yeah, very excited. Welcome. And I'm going to try and admit a few people here as I'm doing this. Okay, great. Welcome. This is another seminar in our series that we've been running for the past several months on complex risk science. And we're, as always, delighted to have everyone here. The refrain that we have and the reason that we've been doing this is this topic requires a community that's unlikely to be brought together elsewhere. And this is meant to be a space for that. So we're bringing people together within these seminars and around these seminars that span the space of what needs to be considered when we do complex risk science. And we're attempting to create a collective that is as plural as it is rare. My name is Ryan McGranigan. I'm a researcher at the NASA Jet Propulsion Laboratory, and I curate these events. And very happy to have everyone here today. So a little primer. We've talked about this in previous seminars. So you can see it's on the YouTube channel that I'll share the link to in just a moment. But we're attempting to address complex risk science. So this is combining the idea of risk, which is likelihood, exposure, and vulnerability, which is a probabilistic characterization of a hazard alongside the quantification of the exposure, whatever's in the way of that hazard, and the susceptibility or the vulnerability. The likelihood that that piece of equipment or that population or something else will fail or be damaged under those conditions. Risk science is bringing all those things together, and complex risk science is doing that by using means of assessing the interconnections between all these hazards and all these systems, so that we can understand what are the emergent properties and phenomena that happen alongside these things. So we've been studying this in a number of ways. Last week or a couple weeks ago, we had a discussion from Jane Baldwin, who kind of took us full scale from the hazard all the way through to the quantification of the risk for tropical cyclones. Today, as always, we're trying to kind of iteratively create a trajectory and understanding and building up complex risk science understanding and capability. So last week, or a couple of weeks ago, as I mentioned, we had Jane Baldwin give a fantastic seminar on tropical cyclone risk quantification, which was outstanding, and it leads very well into the next kind of iteration of the development of our understanding of this and ability to do this, which is taking a full area of interest and first quantifying that first hazard layer, but then, as our speaker today has pioneered, be layering on in a way that doesn't just keep them independent, but actually explores the interconnections between different hazards. How do you start to model that perhaps as a complex network? And how do you start to constitute some of those connections and relationships that exist between these, which is an important next step. So all of this represents our evolving risk science towards complexity, which is an approach that's driven by complexity science, critical transitions, and really understanding and trying to bring about resilience. This requires understanding the interconnections between hazards and infrastructures and populations, and the way that those interconnections change, the way that we understand risk, the way that we map it, and can try to prevent and prepare and generate preparedness for that. So in this process, the purpose of these seminars, the central question we're trying to understand is actually how risk changes when we acknowledge and begin to account for more of those interconnections, and acknowledge the uncertainties that exist within those as well. So these seminars are serving the purpose of bringing about knowledge for how to do that. It's not just one-time interactions, but it's really trying to sustain those interactions to create a more plural community so that we know who to work with when we're proposing new things, when we're working on a new study, where to go for answers for some of the big questions that we have, and to benefit from one another's work as well. The key to this, we believe, is cultivating forums for these sustained interactions. So we have a Slack space, which provides one way of interacting. Everyone's welcome to join there. If I think the link in the chat is the more updated one if you want to grab that. But of course, we have these synchronous seminars. And then there's this idea that a number of us on this call have been working on in various settings called fractal gathering, which is kind of a provocative way of thinking about how do we create multi-scale interactions and interactions across media, whether that's in person at workshops and conferences or online via these seminars or in Slack spaces or others, and how do we allow those interactions to kind of amount to more than the sum of their parts? And so we're really exploring this idea of how do we actually treat the community gathered around as a complex system itself, and cultivate interactions that are really meaningful. A lot of these are leading to artifacts in terms of data analyses or tools or different methods, things that we're trying to instantiate in software and technologies. And so we have a GitHub space where different projects can be proposed and maintained. This is called the Complex Risk Collective. And so a lot of good things are happening there. You can see a couple of projects already exist there and are actively working together. This is the space that we're cultivating the analysis working groups that we've been talking about. So I encourage you to pay attention there and see if you would like to cultivate and learn some things there. So before I get to the speaker today, I just want to kind of punctuate this idea that these seminars are being intentionally designed to build up an understanding of the important elements of complex risk science. So to look at a few of the past speakers, we had a discussion from Roop Ganguly, who kind of introduced us to this idea of complexity emerging from interconnected systems. Then Dr. Sai Ravella talked about how to acknowledge uncertainty and start to account for uncertainty within our systems related to risk, and how the non-stationary nature of the world we're working in is changing that. How do we work with that? Then Elizabeth Kruger introduced us to the idea of socio-ecological technological systems, and how that means we need to change the approaches we have towards risk science. And then just last week, or a couple weeks ago, we had a really wonderful talk by Dr. Jane Baldwin, who talked about pulling these pieces together to actually do complete risk analyses and looking at some of the missing links and predicting future extremes that we need to incorporate into this as well. So this builds very well, and I think today's talk is going to be a perfect extension of this trajectory towards complex risk science, returning us to quantitative analyses, but now informed by complexity theory, uncertainty, and socio-ecological technological systems thinking. I'm very excited to have Dr. Alexandre Dunant to speak to this. A quick note, and I think you'll hear more about this in the talk, but this is also going to speak to some of the discussions and outcomes from a workshop that we held a few weeks ago at IASA, the International Institute for Applied Systems Analysis. This is something that Alex himself was a great engine and thought leader behind. And it was trying to think about how we do risk analyses in non-ergodic systems, or systems whose pasts and previous data may not be predictive of their futures. Which maybe requires a sea change for how we think about these things. But this is a really excellent workshop, and it's part of this fractal gathering idea that we're talking about. So these events are happening. I encourage you to bring yours here and help us become aware of those so that we can keep connecting this community. So today we're going to be hearing from Dr. Alexandre Dunant. Dr. Dunant is a senior researcher at the Center for Climate Change and Transformation at EURAC Research in Bolzano, Italy. Fitting for such an enterprising research institute, Alexandre is a pioneer in bringing network analysis and complex systems theory to the study of hazards and risk. The diversity of his experiences and scholarship suits the complexity of the systems he studies. Something like Ross Ashby's law of requisite variety, I think. But among other positions, he has been an exploration geoscientist at Shell, focusing on offshore and onshore projects in the UK, Netherlands, and Brazil. A research risk scientist at GNS Science in New Zealand, developing probabilistic multi-hazard models, and a postdoc at Durham University, advancing national scale preparedness for catastrophic multi-hazards. And before all that, he received his PhD in disaster risk and resilience at the University of Canterbury, New Zealand, a master's in earth science from Vrije Universiteit, Amsterdam, and a bachelor's in biology from Rennes University in France. Alex and I first met in front of his poster at AGU in 2023, which I still think was one of the most remarkable pieces of research I encountered at that conference. And he was in that paper discussing how he constructed a multi-hazard quantification system based on network science that I think is still some of the pioneering work in that. Since then, he's become one of my most valued thought partners in this space and someone from whom I've learned immensely. So without further ado, I'm very pleased to invite Alex to share his work with us. So Alex, I'm going to hand it over to
you. Yeah, thanks a lot, Ryan, for the very generous presentation. And I want to acknowledge also all your work in this space and to create this platform. I think it's great. So let me share my slides. You can see it?
Yes, we can. Thanks.
Brilliant. So as Ryan mentioned, I've been working on the quantification of multi-hazard risk using network science, and I will come back a bit on the first, my initial step. So I want you to follow me chronologically through this process that I went through as well. So there are different definitions for multi-hazard, I think, and it's still not clear what the terminology is, I believe. But what we know is that we are moving away from a single hazard, where one hazard is considered for the risk assessment. The second step, I would say, is what's called in the discipline multi-layer single hazard, where you indeed take into account several hazards, but they're actually not connected between them. There is no interaction. What I was trying to tackle during my PhD and still now is the multi-hazard modeling, where actually those layers are talking to each other, which of course bring a lot of challenge in terms of the modeling complexity. So from if we want to make it a bit more, let's say, according to the literature, for example, Gil and Malamud that wrote a seminal, I think now is becoming a seminal paper on multi-hazard. How do you move from multi-layer single hazard to multi-hazard? So the first step is the hazard identification and comparison, where we have identified all the individual hazards. And it's also a call by many of the UN agencies to look at all hazards in one place. The second is to have the identification and characterization of the interaction between those hazards. The third one is to take into account hazard coincidence, when two or more hazard coincide spatially and temporally, so that the result, the risk might differ from the sum of its parts. And the fourth point is the dynamic vulnerability, or how through a series of hazards the vulnerability changes in time over like shorter or longer period of time, and it basically makes the risk differ. According to this definition, that's where you reach multi-hazard. It's also it's a goal that's hard to reach, but we'll go through this. So I thought I will also provide a look back at the literature on multi-hazard, and there was this very nice paper by Taylor in 2019 when he looked at what was actually the literature telling us about what the work was happening in the multi-hazard space. So you can see that few papers between 1990 and 2000, that's very the beginning. But I think what changes things are the tsunami events from 2004 to I think 2011, to be honest. So 2004 is the big Indian Ocean tsunami. So you can see it almost as a cascading processes from the initial earthquake, and that killed more than 220,000 people. Then there is the Chile tsunami in 2010, and followed the next year by the Tohoku disaster, where you've got an initial earthquake that trigger a tsunami, that then trigger NATEC issues with the nuclear reactor in Fukushima. So I think this is where you see the publication and research ramping up, probably related to an increase in funding as well. In the same paper, I found this actually figure fascinating, because and it's talking also to the complexity of actually doing hands-on modeling in this space, where you can see that among the publication, 45% only are actually trying to attempt modeling, whilst most of the other part is focusing on the terminology. With, I think, even though there are some consensus about the terminology, I don't think we are there yet. There are still a lot of discussion of what multi-hazard is, but I will more focus on the 45% in this picture. Just to put a bit more confusion into the mix, I think there are two different maybe communities that maybe don't use the same terminology. So on the one hand, you've got IPCC, climate change. On the other hand, you've got DR, which is maybe a bit more geo, so seismologist, geomorphologist. And I think the terms are slightly different, the concepts are slightly different. For example, term like impact or risk could be seen differently. So it's just something I wanted to point out, and something to keep in mind. So there was a recent review by Owolabi Sajad, which actually looked back at also what was the term used in the multi-hazard literature. So it's quite recent, 2023.
Well, we're supposed to do that. You do that in the paper, but you do that, but we have.
And so what you see is really a focus on risk assessment with a strong component of geomorphology, because I think this is a bit where it started, and also it makes sense because landslides are always triggered by something. Mass movement is triggered by either earthquake or rainfall. So it was early on in this space of multi-hazard, I think. From the country where it's originated, I was surprised to see Italy has a big blob. So but the US are there as well, China, with a strong connection within Europe, and also between like France, Italy, and the US. So I want to talk about a bit the argument to the multi-hazard, because it could be basically it was a demonstrated, I think, by some events, but I think there are some the main argument to talk about multi-hazard was really that if you don't take into account those different interaction, then you will be basically missing a lot of the risk that could be triggered by that basically will be completely invisible by single hazard analysis. And that was the point by Capes et al. In 2012, also becoming a seminal paper, a classic in the multi-hazard literature. The reason for that is that you increase the vulnerability to other spatially relevant hazards. You distort management priorities. For example, if you focus on earthquake without looking at the flood, these kind of things. And overall, you just underestimate the risk. The publications, there's a long list of publications about this feature of the multi-hazard risk assessment. Another more concrete argument that was made in 2023, I think by the team in Amsterdam, was to look at all the global database that we have and trying to somewhat merge temporally and spatially the impact that were observed all around the world. And what you can see is that actually a big part of the world is subject to multiple hazards of different type and different magnitude, but it means that it's at least something that should be considered by research, and most of the area of the world are actually subject to this. Of course, there is the argument about more like the discrete but massive event where you see, for example, in Kaikoura, New Zealand in 2016, where the initial earthquake actually destroyed one house, but the consequent landslide blocked the whole road system for quite a long time, causing millions of dollars of loss because the transport just couldn't go from the south to the North Island. The Wench one in 2008, where the initial earthquake caused damage and issues, but you had consequence like, for example, the landslide dam that was triggered that provoked the evacuation of about 150,000 people and were a threat to 2.5 million people downstream from an outburst flood. The Tohoku, we discussed already about it, where the initial earthquake triggered a tsunami that triggered an issue with the Fukushima nuclear reactor. And another example in 2018 is Anak Krakatau, when the initial volcanic activity provoked the collapse of, I think, 2/3 of the height of the island. So a big part of this volcano went into the sea, creating a tsunami that killed about 400 people. That was completely missed by any warning system because of this cascading process. So in 2021, I wanted to make a bit more of an analytical argument using a bias variance trade-off that is used often in machine learning, whereby if you've got low variance, you're underfitting. If you've got too high a variance, you're overfitting. So the idea was that if you look at on the right side of this slide, where if you are in a single hazard model, you're at the bottom row, and if you're in the data-rich, even if you're in the data-rich model, your model is highly biased and might not represent the center of this target, which is the true risk to your community, to your buildings, and so on. So the argument was that through multi-hazard model, it was a low-hanging fruit that we didn't need maybe to. I mean, we still need to have more data for sure, but in a world where most of the natural hazards are actually following power law distributions, and really damaging impact data is actually quite rare to come by. So one of the advances we could make in terms of targeting the true risk was really to go to this multi-hazard model to actually reduce the bias of our models. So for anyone who has attempted to do multi-hazard modeling, there are a set of challenges. Once the hazard have a wide range, a wide spectrum of spatial and temporal scale. And normally in the risk modeling, what has been done is we use a qualitative method to combine those hazard and risk together, or semi-quantitative method using, for example, indices or dollar loss at the end as a way to combine the effect of those hazard. Even though I think you underestimate, as I will show you, I think you underestimate the risk if you don't take this interaction into account. It can't be a process that's done at the end in the risk space. But one of the issues is that if you try to combine multiple physical models, that you're a bit bounded by the computation, even though it's improving, but it's still hard to go from one software to another software and pipeline those together. Could be a bit clunky and inflexible. If we want to do joint probabilistic distribution and use, for example, copulas, we need data. A lot of areas in the world don't have this kind of data. Some methods can be used, but there are limits on the number of hazards interacting, and some others are purely, let's say, statistical tool without spatial output, and spatial output are often required by emergency services. So I started to look into what was done a bit somewhere else and bump into the complex system science through where they use it to analyze either social network ecosystems, but also infrastructure network. Already at the time, they were already working on graphical methods to connect electricity and energy sectors, these kind of things. So the idea came that a graph could be a great way to actually represent this interaction in the landscape. So you can see, like, graph theory is not new. It's pretty much dated from the 18th century by I think the Seven Bridge issue done by Euler. And so the idea was that if we can conceptualize the element of the risk we want to study, then we can represent them as nodes and edges. But on those connections, we can also extract the GIS information, either from rasters or shapefile that we need to actually understand how the interaction can propagate into risk. In this sense, then the risk doesn't become a burden to the hazard modeling, but it's actually an opportunity to constrain your landscape to only what you plan to do. So there is an action that needs to be fulfilled for someone, for a purpose, and actually the network is designed in this way. So it's intention first, and then you design your network. So early on, there was at the time the Kaikoura earthquake happened in New Zealand, so quite a large magnitude earthquake with a lot of issues on the road because of the cascading effect of mass movement. And we thought, well, let's try to have this toy model to see if there is some positive result out of it. So we thought about, at the time, simply just to use, for example, slope unit as a potential representation for the nodes. We spaced the road into multiple nodes, And we used a nominal node for earthquake and rainfall because the effect was so regional. It didn't matter really where the earthquake was compared to other nodes which we thought needed to be spatially explicit. And then we based on the expert consultation, we basically connected those nodes. So the idea was that rainfall is probably not going to trigger an earthquake, but an earthquake could trigger a landslide as well as rainfall. So on the left side, we build the network in a special way, but it's a bit messy. So we represented using the tools like Gephi that they use in biology to represent it in a more abstract way, but clear way as well, where you see really the earthquake node being the central node of most of the interaction, as well as the rainfall node. And you can see like some of the nodes connected to many. It's often when the slope unit could be connected to several road nodes close by. So the idea is that I explained this network creation where we actually put the hazard information onto the edges. So we can start to have this network, which is a relatively light structure. Actually, at the end of the day, you can represent it as a relatively massive Excel spreadsheet, which is still lighter than having most of the grids and shapefile actually. So we thought, okay, let's generate scenarios. I will show how we did, but basically the idea is to spread an initial signal through the network. Once you reach the end node, then you start all over again into a Monte Carlo simulation. Once you reach convergence, then you get the database output that you can then analyze. So the probability come at the end, not at the beginning in a way. So once all the information was on the edge, we thought, well, let's use some kind of a gate system where you move from one node, and if you want to go to the next, you need to pass a gate. That's often associated with the random number being generated and compared with the value. If there are accidents, then you move to the next node and so on. That's how we propagate in the network. So I found this simulation. It's for the spread of a pandemic, but basically it's kind of the same idea where you start from one point and then you spread along the connections until you reach the terminal node. And in this case, our model will start all over again with sampling different branches depending on their likelihood. I have to say the initial model was a bit harsh. There was very little fuzziness in the model, so it was either you're like beyond the threshold or you're below it. But what we thought when we studied the road compared to the road service state, and you can see on the right the different segments of the road where the model was giving those blue like histogram bars, and the actual impact were actually the red bar, and it gave us confidence actually it could work potentially. So we sort of at this point moved to the next step and thought, well, let's try to build something maybe a bit smaller but more complicated, more interactions. Let this time be based more on the empirical relationship that we have in the literature. And we decided to use to go to the Franz Joseph Township on the west coast of New Zealand, where I mean, you can see on the picture there that it's quite subtle, but there is a bump on the road there. It's one of the largest faults in New Zealand. The Alpine Fault is running straight to the village. And in the back, you have really steep slope with about 10 meters of rain every year. So it's monsoon kind of level of rainfall with the associated landslide and mass movement. So the idea was to build this model where we combine earthquake, rainfall, landslide, the potential for landslide dams that could create floods, but we put some rules about how an earthquake could impact the stop banks as well because of the horizontal movement. And you can see the graph represented again with Gephi on the right there. So the output could basically maintain the coordinates of the different nodes. So it was relatively easy to get the get the output as a special assessment of the risk. And we wanted to show also that we could do some qualitative results for the village that was quite keen to have these kind of things. But we did also a full probabilistic assessment that you can see on the left-hand side, and we compared to, so what would be the result of multi-hazard versus taking single hazard. And what was interesting, if you follow the multi-hazard line, is that at some point you see that the earthquake magnitude actually doesn't matter anymore. Everything that can be destroyed by the magnitude 9 will be destroyed, and but you see the multi-hazard line continuing. So we thought that you have like amplification of extreme losses that was completely invisible to single hazard assessment, but you've got also an accumulation of weak losses. So there are more events happening in general if you take into account the combined effect. It was pretty clear that the reason was that all the earthquake models that went into it were actually supercharging secondary effects, such as massive landslides, larger landslide that would actually impact what was remaining of even the larger earthquake. So it was interesting. And when we did the risk assessment, we realized that for the township, it was in terms of standard, it was way below what you would expect for a touristic town. So compared to for example, what they have in the Netherlands, in terms of risk to flooding and this kind of things, where this risk was way too high for a touristic city. So now we jump into Nepal. So a bit of a different setting, but so at this time I moved to the UK, and we wanted to work on the contingency plan in Nepal. From a request from the UN office, because they said, well, we've got this earthquake model that actually generated a good result, but the problem is that we often see landslides happening with the earthquake we have in Nepal. I mean, it's a good reason, like Nepal's valleys are very, very steep. So could you actually build a multi-hazard model and do your research, and at the same time inform the next contingency plan? So that's what we started to do. So the idea was to look at the earthquake and the follow-up landslides, and what could be the impact on the roads and building, and continue doing the research on this graphical approach. So in the context, we also run a series of workshop with the humanitarian team there, which is it's a cluster group of NGOs that would tell us also what was interesting for them in terms of the timeline, where did they want to have the information, at what scale, temporally and spatially. And there was some interesting insight that actually maybe the most precise model was not what they required. We're also surprised to know that actually like casualty estimate was not really interesting, but injury estimate was interesting. So this kind of, I thought I would mention this kind of feature as well. So going back to the graph, so on the left, you can recognize the graph that I mentioned before. So a directed graph. But because Nepal is a large area, we had, if we took the same approach as we did in New Zealand, it would be about 7 million nodes for the building, and a bit more than 3 million nodes for the road segments. So we thought, okay, let's rethink the framework a bit. And what came up was that we could use hypergraphs to reduce the computation. So the idea of an hypergraph is that instead of being bound to pair-to-pair relationship between the nodes, you could actually have one-to-many connections, because you use the surfaces to connect the node together instead of just lines, which, looking back, is a lot more logical if you use like polygons on the map, for example, or slope units. What you see at the bottom of the table is an incidence matrix that is a representation of the graph above. And you can see that if you use the hypergraph, suddenly the graph shrinks, which means that the computation get that much faster as well. So back to back up this simulation, we also used all the engineering surveying that was done at the time with a brilliant project, I think, which is called Meteor, where they tried to survey across the whole Nepal the building typology. So then we could use, in addition to the multi-hazard graph, we could actually sample those fragility function to give an estimate of high, mid, and low case. What we looked also was how to manage the injuries and fatalities, casualties from the landslide perspective, because what we realized is that we might not be able to do it. And one of the reasons was through this publication with Max van Beek de Vries, we looked at there was a correlation between the number of houses affected by landslide and the number of human loss. And basically, you can see that the eye color is right there in the middle, where you would expect it completely at the bottom right. So there is not really a correlation. It's not because you map the risk to the buildings that you can make this transition to casualties. So in the same way as we did before, we've got this initial earthquake node that's very much like nominal. It's just a regional pattern. And then you spread it to the connected nodes. In this case, that would be the buildings and the slopes. And when you reach the building, that's pretty much where the assessment on the fragility using the fragility function is done. But when you reach the slope, then you've got a randomization exercise using the susceptibility of the slope. And then you propagate it if you pass this gate, let's put it this way, to see if there is an impact on the buildings, on the connected buildings, or on the roads. So what we thought was, okay, we have got this theoretical framework to use hypergraphs. So I think one of the obvious candidate to test it on was the Gorkha earthquake in 2015, where 9,000 people died in Nepal. And so we decided to use it as some kind of a validation test. So it's a bit of a busy slide, but basically what you can see at the top is an estimate of the number of buildings that we expect to be completely damaged, with a range based on the fragility that we had, and the points actually where the actual event fall. The second line is the relative error, and you can see that there are some. I mean, even though the model we're relatively happy with, there is some movement around this line, and we think it's mainly related to actually the shape of the ground shaking that we believe was more elongated than what was in the model. But I think the validation for the whole PGA field was done on one station because the other one was not working. So there is a lot of uncertainty going on in Nepal because it was hard to constrain. And you can see at the bottom basically the distribution of the different building types per I think ward at the time. On the right, you can see that that's the prediction. The colors are showing the prediction for the landslide risk for the buildings and the roads, and you can see that the cross is where the actual event occurred. What's interesting is that you could all this is coming from one model. There is no two models. It's all coming from the same output. So that's I think the strength of this multi-hazard approach, where everything is combined. It's just up to you to untangle what you get at the end and the impact that you get at the end. So the next step from there was to think, okay, the model is very quick. Like we're talking like 15 minutes to do to reach convergence on this model at a national scale. So it was extremely fast. And I think a lot of work was actually creating the network early on. So we thought, okay, let's take 30 different historical or likely scenarios for the potential future earthquakes, and then run those as an ensemble, a bit like what climate science is doing. But and observe the cascading effects of each of those ensemble members. So what we got at the end was also a probability assessment that we could do, for example, per physiography, which was interesting and valuable, I think, for the UN office there as well. We could have the result as maps in terms of not only the absolute numbers, but also the percentage of impact for either like earthquake on buildings, landslide on building, and landslide on roads, and also the deviation among all the ensemble members. So really moving this cascading multi-hazard model into the where I think the climate data is a lot more familiar with. An interesting feature, and I think it would be relatively hard to get this out of a single hazard model, is when you combine those two together, because we have to remember that for each ensemble member, like shaking is completely tied with the mass movement in this case, because it's just how the model is built. We saw that if you look at the building damage is showed in gray, so it's sorted, and the damage by landslide is shown in blue. And the interesting thing is this red line that show you the landslide to shaking damage ratio, and it seems to be almost reversed. And I thought that's very interesting, because it's showing almost like a duality between highly populated urban areas and more rural side, where you would expect on the rural part a lot more impact from actual landslides and a lot less from earthquake, where in the urban center it was less. So I think I did a bit of digging, going back to like old books that I read from Jared Diamond about geographical determinism, because I think it's also related to the developments where you have the tendency to settle in basins that are accessible, and then further later on in the development of the countries, I would expect then you move toward more steeper slopes. So the question, and I don't have the answer to this, but the question is, does it apply to any seismologically active mountain in the world, this kind of features, this divide between urban and rural in terms of risk? Another thing that we looked at was like a report from the World Bank created the remoteness index for Nepal, and because we had the damage to the roads from our multi-hazard model, we thought, okay, let's compare how the remoteness compare with the potential for damage on the roads. And you can see that there is a compounding effect on the right, where as the percentage of damaged road increases, you can see also that the remoteness is higher. So you've got this compounding effect. It's not only that they are further away, but they are more likely to be blocked also by landslide. So if there is intervention to be done, you've got this sort of accumulation effect where it's just going to get harder to get support. So recently we have been looking also in New Zealand at a model using a graphical model, but to make it dynamic, because at the moment what we have is very sudden burst of events along the network, which is very much instantaneous or semi-instantaneous. In this case, we really want to see like long-term, over years, the evolution of a precipitation model with volcanic eruptions, because volcanic eruption has a direct impact on the hydrology. As you can see on the right, if you've got like pre-disturbance and post-disturbance, so post-volcanic eruptions, you can see that the overland flow increase, the infiltration decrease, and we built a model that was like fully dynamic on a daily scale. to see what would be the impact. So on the left, you can see a summary of, so you've got the rainfall at the top, you've got the water discharge in the middle in blue, and some burst of event that could be like deterministically or randomly attributed. But what's interesting on the right is that if you look around like peak rainfall events, you can see that the discharge actually massively increased with in a post-ash world, let's put it this way. So there will be a big compounding effect of this interaction between the river and volcano in the case of an eruption. At the moment, it's a toy model, but I thought it was giving some interesting idea and pushing also the graphical model into more of a dynamic model. So now I'm back to the multi-hazard argument and actually trying to probably shoot myself in the foot there, but I think there is a lot of push now for multi-hazard. It's a bit everywhere, and people are getting more and more complex model, which are also facilitated by better access to computation. I think we have to be careful, though, that following my initial argument about the bias-variance trade-off, I don't know where we are compared to the optimality of prediction in the modeling, but I think it can apply also to participatory interactions, where you could move maybe in this space where actually like the variance is going up again when we try to build model of everything, and we've got participatory interaction, what I call like too many cooks in the kitchen. I think it's just I thought I would provide this word of warning because I see that there is a lot of appeal for multi-hazard, and I think it's as I've shown it makes sense. But I think also that we have to be careful that the study of actually the underlying uncertainty propagation complexity metrics is not tracked at all from what I see now. I mean, we mentioned it before with Ryan, but we started to discuss also because I think there is it is true that complicated is not complex as well. So this ergodicity problem, especially if we move into longer temporal framework like climate science, for example, is an issue because what you have known in the past might not be what you see in the future. If you take the time average, might not be equal to the ensemble average over your system. So you might have those ergodic system, which I think in the risk equation that's used normally, like hazard, time exposure, time vulnerability, change a lot between the terms of this equation. I think you can imagine that in the 1970s, predicting the climate of today is a possibility. To predict TikTok and cell phones is a bit harder. And I think it's something we have to acknowledge that we might be just mistaken by quickly multiplying those factors. It might be fine for buildings, but if we start touching at social system, then it might be a different beast altogether. And I think also the scale is something that's often mentioned by social scientists and physical geographers as well. As soon as you zoom into the layer spatially, then you start to see new things emerging. It's not the same thing. It's not only a change of quantity, but it's a change of nature. And I think it needs to be acknowledged as well. So to do so, we have, as Ryan mentioned, this YASA workshop last month, which was a brilliant event in my book, and where we discussed a bit around those things and really to put complex risk on the table and on the forefront of the next challenge for research. Yeah, I'm done, Ryan. Thank you very much.
Thank you so much, Alex. Fantastic. So I've been putting some things in the chat to try and keep track of resources, and welcome everyone to join in the discussion. Either put your comment in the chat or just open your mic and feel free to ask Alex directly. And I'll get it started while people are thinking of that and figuring out how they want to term it. I'm very curious about the formation of the network. And so you have a few things contributing to how you understand that and how you initially kind of compose that. One is, data driven. There are we can unearth these empirical relations based on historical data. Maybe those are published in literature and you can find those. And so those form your kind of well-known interconnections. And then there's expert elicitation. So you ask them, what do you know from this system from analyzing this? So how do you allow that system to grow? Because inevitably your network's going to be incomplete. Do you try to learn new connections, or how do you approach that problem?
For now, no, but I think it might be the next. Actually, I'm really curious about the explorative capacity of those models. So because I was requested often, because it's really one issue is the time you spend to build a network. So that's one argument to actually have an explorative network. So you gain time. The second is to avoid biases. So basically, you use the empirical relationship, what you know, maybe machine learning models, to actually that the network discover the landscape in a way. I think that would be a great follow-up work.
Very cool. Thanks so much. So I see Sama had a comment. I don't know if Sama is still on, but if you want to voice that comment, Sama, please feel free. If not, I'll open it up to questions or comments. Yeah, Daniel, please.
Hi, I'm Daniel Illuminati. I'm the Chief Engineer for Earth Science at JPL. Nice to meet you. That was a great talk. One of the questions we have as we move into the space a little bit is understanding how much effort is required to put these models together, kind of what you were just hinting at. Are there metrics available or rules of thumb for, if you want to do a multi-hazard model of the Los Angeles area or Southern Italy, whatever, right? Like for how many hours of effort, what kinds of people you need, planning tools for how to scope that work?
That's a good question. It's very dependent on what you're trying to model. I would say that Los Angeles is a big area. I mean, if we're talking fires or these kind of things,
well, we have earthquakes, fires, floods.
Yeah.
I mean, like it's kind of like Italy, right? Like all the
yeah,
almost everything except for hurricanes, right? So yeah.
I think it's so it depends a bit what you need to have some sort of a list of the interaction you want to map out. From there, it's not too much. I think I was pretty much doing it on a one-man army, but I think I would do it in a couple of months now. Because especially if you have people that can just automatize the creation of the edges, at the end of the day, it's an Excel spreadsheet that you're trying to create. So I think if you've got good computer scientists, it can be relatively easy. The issue is really to understand the connections, because if you have flood models already that are available, I will try to maximize the connections to the largest even possible. Because what you don't want is to have connections that don't exist and should exist. So that's a good way maybe to reduce time, is to take the worst case scenario and connect your connection this way. So you've got already an initial network that's built, and then you can trim it from there. Hopefully it doesn't take too much computation to do so. But I think it's less of a problem nowadays with like lazy libraries and these kind of things. Yeah, I don't know if it was informative because
it sounds like that was useful. Thank you. It sounds like maybe order of a work year or a significant fraction of a work year for a place the size of LA or something. Maybe for a multi-hazard model, like that's at least an order of magnitude, right? Kind of. Yeah.
Yeah, I would say like solid 6 months. I would imagine.
Yeah. Okay. Yeah. Thanks.
Excellent. We have a few more minutes if others have thoughts or questions. So Alex, while people are thinking, I'm curious about how you actually engage with, who you define as an expert and how you start to incorporate that into the model. So like the empirical relations are pretty straightforward to encode, but how do you coordinate that speaking with the people who know and then trying to actually translate that into a model?
Yeah, I think it was. I mean, so far it was pretty straightforward. Like we had policymakers that wanted to answer a question, and they have seen many events in the past, and same thing for communities. So they have a ranking in their mind of what the interaction are. So, for example, in Nepal, it was pretty clear that landslide and earthquake should be part of it, monsoon and landslide as well. So that's why most of those models are actually pretty shallow, I would say, in terms of the network depth. So they're a lot more horizontal. Let's put it this way. But if you move into a different space, maybe working with infrastructure providers and these kind of things, then you might be able to do things a bit more in depth, because at the end of the day, I think the strength of the tool is really that you move this landscape, a natural world, into a network, so you can connect it to other network pretty easily. Could be electrical grid, but could be also a social network potentially.
Yeah, really interesting. Thank you so much. And I'm also, it's very interesting. We've done simulation games or tabletop exercises to start to uncover. If you put people in the context of an event unfolding and then see who they talk to and what data they require or would like to have, that seems to be really important to kind of emerging those unknowns that we kind of would need to quantify that aren't often. So that's very interesting too.
Yeah, I have to say that I have to give credit also to all the social scientists I work with, which were always part of the projects, pretty much.
Yeah,
So yeah.
that's an excellent point. We do have one more minute, so I'll leave it open for just a little while if others want to get something in. If there's nothing, I will make sure I update the resources on the website, and I welcome everyone to join the Slack and continue the discussions there. But please join me in thanking Alex one more time. This is a fantastic discussion.
Thank you.
Thanks, everyone. Have a great rest of the day. We'll reconvene on December 2nd.
Uh,